Welcome to part 3 of week 4, and this is the final part. Jumping over to FM radio now. So we started with police radios, which were AM. We talked about microwave, which can be AM. Now we're going to talk about FM. So what's AM and FM? AM stands for amplitude modulation. FM stands for frequency modulation. Won't get into the technology behind it, but it's much better. So in the mid 30s, Major Edwin Armstrong, we spoke about him back, I think, in week 2. He mentioned that he was a creator of a very significant AM radio, quality radio, but he realized there were problems with the AM radio. It had interference from household appliances and lighting. It had very poor audio quality, all things considered, when you get technical, the frequency response and dynamic range of the sound. Nighttime interference from other stations, also co-channel, meaning somebody who's close by on a frequency. Particularly at night, if you again listen to AM radio, you can pick up stations from thousands of miles away, and during the day you're doing well to pick up a station from 50 miles away. That's got everything to do with how the atmosphere refracts, reflects, and absorbs radio signals. So he's looking at all this and he's thinking about it, and he goes, there's got to be a better way to transmit radio. So he did a way of encoding the audio to eliminate these problems, which ultimately became known as frequency modulation radio, or FM. He had a good buddy of his, a guy by the name of David Snarnoff, who happened to be the head of RCA. Hey, what? You got friends in high places? He goes to David and says, hey, this is cool, right? So what do you think? Well, Sarnoff goes, I want to help you develop this. This is pretty cool. So RCA bought the patent that Armstrong had created, and they built an experimental radio station. But it became evident to Armstrong after a short period of time that they weren't really interested in working with him. They were trying to protect their existing AM radio businesses because they'd invested a lot of money in AM radio transmitters and radios that were being sold to everybody and their brother out there at home. Not necessarily in the car, but everybody was at home. So they didn't want competition from this newfangled form of radio. They had invested a lot of time and money in the AM side. So they essentially bought his stuff to kill it. So they tried, and they closed down the FM station that they'd built to help him do this, and he went in there all sorts of costly legal battles, which Armstrong could not begin to win because RCA had much deeper pockets. Believing in his invention, he went off on his own and did some further advancement in the FM radio to create some new patents that he could own, and he sold the right to manufacture these radios to many other companies, excluding RCA. So within years, 1941 to be exact, there were over 50 FM stations on the air. Then World War II happened, and all the resources were frozen, and the development was frozen. All was focused on the military side of things, which, we could spend hours talking about the technology advances as a result of the technology needs for World War II. There was a terrible war, but the technological advances both in communications and transportation were massive. At any rate, the war ended and television started to evolve, which we'll talk about in a future module here. Interest in the FM radio was diminished. And from most perspectives, by 1949, most of those stations had all shut down. It's like, okay, that's cool, but TV's the new cool thing, right? Armstrong never got to live to see the success of his invention. Sadly, he had actually took his own life before things got further along because he was broke and destitute. We never will know what he could have done. It was really kind of a sad situation. But his brainstorm, his creativity created the FM concept. And at the end, RCA started developing its own stuff and made millions of dollars as a result. But FM's important because FM is also a key methodology of how we deliver our communication services. Now we're going to talk about the transistor. Arguably, some feel it may have been the most important invention of the 20th century because its impact across every aspect of our lives, from anything involving electricity, it is huge. It drove to the integrated circuit, and from there we keep going. So how did it all happen? Well, we're going to go all the way back to 1907 again, to AT&T, and the fact that there was lots of competition happening, and amongst many other things that was going on, then President Vail of AT&T thought, how do we compete with these little phone companies? Well, let's create transcontinental telephone service. And we've talked about this before. Very expensive, and it took them many years to get there. We also talked about DeForest back in week 2 when in 1906 he invented the vacuum tube, or a triode vacuum tube, which is, we'll get what's a triode versus a diode, but at any rate, the triode by its nature could allow you to amplify signals. And they could amplify signals from phone lines. And so what AT&T realized is they could use this patent. So they bought the patent from DeForest and they made a whole bunch of improvements in the tube, and they essentially created amplifiers that would be installed along the long circuits or the long lines they had going between major cities and amplify the signal as it got weaker. So this allowed you to increase the distance that the voice could carry from one point to another. There were a lot of problems. Even though they really did some amazing work, some of the issues were tubes draw a tremendous amount of power. Secondarily, they create a tremendous amount of heat. The old tube televisions were phenomenally heat generating. The old radios were very warm because the tubes were like light bulbs in some respects, so they made a lot of heat. And on top of that, tubes burn out. And so there was a huge amount of maintenance, high electrical bills, and issues with heat management at these switching centers, if you will, or these amplification centers that AT&T had designed. So in the 1930s, the director of the research at Bell Labs, a guy by the name of Mervyn Kelly, recognized that they needed a new device. They needed some new way of doing this, and he began to have his team research and explore a new class of materials called semiconductors. Now, Bell Labs, pure research, amazing place, and in the course information in the content section there are going to be links to the history of Bell Labs and stuff if you want to spend some time learning about the history of so many things that impacted us. Bell Labs was just an absolutely amazing place. So the team worked on it, and after World War II ended, he then created a new team of scientists to work on these solid-state semiconductor devices that they had begun researching in the 1930s. There's probably a lot of research that was done during World War II as well that was probably confidential, classified, top secret kind of stuff. All of that was available as a base of research to work on this. So as you can see, that they tell you what made radar work, which we won't spend a lot of time on it and its impact in the war, but there was a scientist by the name of Bill Shockley. And Shockley was really a brilliant man. And so they made him the team leader. He was a theoretical physicist. He thought in terms like, what ifs, and I mean, I can't even wrap my head around how theoretical physicists think. These are like the Einsteins and the Fermis and other brilliant minds. And Shockley was one of these. So he asked a guy by the name of Walter Brattain, who could build and fix just about anything at Bell Labs, to join his team. And he also hired another theoretical physicist by the name of John Bardeen, who came from the University of Minnesota. They also hired a bunch of other physicists and chemists and engineers, and they sort of created, I'm going to use the term of skunk works, which is sort of an aeronautical term, secret place where they could work and design in the labs this new semiconductor kind of thing. So in the spring of 1945, he came up with, I'm sure working with his team, the first semiconductor amplifier, because they discovered something called a field effect, and we won't even go there. But the field effect allowed this semiconductor material to potentially do what they were looking it to do. It was a small cylinder. It was coated thinly with a coating of silicon. It was mounted to really close to a small metal plate. Well, it didn't work. So Shockley said to Bardeen and Brattain, go find out why. Right, as all brilliant theoretical physicists should do, I got an idea, you go figure out how to make it work, because they know it's going to work if you can get the mechanical issues or whatever the things out of the way. So there's an author by the name of Lillian Hodson who wrote a lot about this, and according to her, in the fall of 1947, Brattain decided to put the whole thing in a tub of water. I don't know why on earth, if you're sitting at your desk or your research bench and you're looking at this going, let's put it in water. Where did this brainstorm come from? I don't know. But it kind of worked a little bit. Something changed because of that. And so he began to experiment, and again, here's this leap of intuition. by using gold on the germanium. Germanium is a semiconductor material. Essentially, it eliminated the liquid layer. The theory is that the layers of crystals things were slowing things down. You can read all about this if you want. Still didn't work, but they continued to experiment using the design as a starting point. So again, late in 47, he had the aha moment. And it turned out they didn't really understand how electrons worked in crystal. Semiconductors are crystals. They didn't understand it after all. In fact, what they were doing was forming a barrier on the surface. So the aha was what they needed. And without telling the team leader, Mr. Shockley, or Dr. Shockley, they worked on a new idea, and on December 16th, they built what was known as a point contact transistor, using strips of gold foil, a plastic triangle, pushing it down on a contact with a slab of germanium. So they called up Shockley, really excited. They go, "Bill, guess what we've done? This is great." So he was happy and furious at the same time because he wasn't directly involved. And, in many ways, researchers work on this pure theoretical work and work on creating inventions and things, but as much as it is the adventure of the exploration and the discovery of solutions, there's also recognition involved. Those prestigious Nobel Awards and those prestigious other recognitions are always sometimes a driving factor. And Shockley wasn't a part of this. So he decided to one-up these two guys. So on his own, his device he created on his own, developed it first off thinking about it for days in a hotel room in Chicago. He came up with what was known as a junction transistor, as opposed to a point contact transistor. So this junction or sandwich transistor took him more than 2 years after he thought and thought and thought about it to build one. It was much more rugged, much more practical than the one that Bardeen and Bretaigne's had created, the point contact transistor, and a lot easier to manufacture as well. So because of this team of brilliant researchers was kind of torn apart, and it really created a whole set of problems as to whose names should be on which patents and so forth. But at the end of the day, Bell Labs owned the patents because they all worked for Bell Labs. And so on June 30th, 1948, Bell Labs settled on the name of transistor, combining the ideas of transresistance with the names of other devices like thermistors. I'm sure there was a research group who spent time working on the naming. But anyway, that's how the name of the transistor was born, and that's how the transistor came about. So I got very little attention outside the researching groups. Like, okay, well, that's cool and that's neat, but we'll just keep this inside the phone company and not do much about it. Shockley, though, realizing that this is a tremendous invention, he left Bell Labs and founded Shockley Semiconductor out in Palo Alto, California. And he hired the best of the best to come work for him. But he also he was a hard guy to get along with, evidently. And so as a result, after a period of time, 8 of his best and brightest left Shockley Semiconductor. And they founded a new company called Fairchild Semiconductor. Now, if you are into hobbyists, electronics, and things like that, some of these names are going to start sounding familiar. Fairchild Semiconductor was one of the first companies in the 1960s to start doing semiconductor manufacturing. 2 of the 8, a guy by the name of Bob Noyce and Gordon Moore, went on to form a little company called Intel. I think we all know what Intel is. And Moore is also very well known for the famous thing, Moore's Law. Google that. Look up Moore's Law. It talks about how much smaller semiconductor technology can get before it will reach its finite capacity. And we haven't reached it yet. 2 more guys, Noyce and Moore, later on Noyce and Moore, working with a company called Texas Instrument, co-invented the integrated circuit. Wow. So you can see here why the transistor's invention and these brilliant men who worked on it led to such an incredible explosion of technology development in the last half of the 20th century. And moving to Palo Alto with Shockley Semiconductor, which nobody ever heard of, was the beginning of Silicon Valley. Had to put up some pictures here because my voice is boring at this point. On the left, you see a replica of the first transistor from 1947, that point contact transistor. And you can see that'd be kind of hard to manufacture in bulk, and it's a little spacey. It takes up a lot of space, but this is from Lucent Technologies back in 50, well, it was the 50th anniversary of the transistors, so 97. At any rate, that's what it looked like. Kind of interesting, kind of homebrew. And then on the right side, you just see some what we call schematic diagrams of typical transistors from the day back then, 60s, 70s, where you had discrete transistors that were used. These are different styles and types, so you can see the significant difference from that unit there, which doesn't require the glass bell. That's just there to kind of protect it from dust. The original transistor to what it evolved to. Wow, we are done. Thank you for your patience. It's impossible to discuss all the technological and regulatory impacts of the first 60 years of the 20th century. We really hit key points without going too deeply. Maybe I went too deep in some areas and not deep enough in others. But I tried to give you a sense of things that were driving major impacts, such as the transistor, such as the development of microwave, such as the development of FM radio, and the regulatory impacts of the government helping to control and manage how radio spectrum was used, and helping to control and manage how phone companies could interact with each other without causing great harm to the public. So it's a lot to take in. And a lot of things you could go ahead and research. There's going to be some cool videos that are in the content section here, talked about the touch-tone pad, the history of the transistor, and some other things that I'm going to toss in there that you can use as follow-on materials. So thank you so much, and we will see you next week.